Okay, this is chapter 2, part 4. We left off last time talking about variation in samples or sampling variation and how, remember, we used the ISU example. If we were trying to take a sample to figure out what the students' attitudes were about online versus seated courses, that if we were to take several random samples, one after the other, of 100 students, that we would get somewhat different results each time because there is this random element to statistics where it's not going to be exactly the same every time. So that's what we mean when we're talking about sampling variation. Now, sampling distribution is closely related. And what we mean by that is if you laid out the results of many samples from the same population, it would begin to look like a bell curve or a normal distribution. So let's back up here a second and you can see an example here. Across our x axis is minutes. And so this is, let's say that this is data on how long it takes workers to complete a particular task. And you can see there that the average is around 10.5 minutes to finish some job. But you can see that some people can do it quickly and just might do it in 3-4 minutes, and some people might be slower and might take 17 or 18 minutes to finish it. So again, the y-axis is not shown here what we mean by that, but that's talking about sort of, how many samples are in a particular spot. So the taller the curve is, the more samples that are at that particular level that they've been stacked up. And when I say samples, I mean the mean from each one of those samples. So this is a little bit complicated because we're talking about a higher level than one higher level than how we're normally talking. So let's look at these curves so you can see what I'm talking about. If you were to just grab a handful of workers, let's say 20 workers, that was a sample, and you grab the first worker, that first worker is, who knows, let's just say that they take 12 minutes to do the job. And then we grab the second worker, and it takes them 8 minutes to do the job. And then the next worker takes 10 minutes. And then the next worker takes 15 minutes. And we lay out each person's score on this x-axis. And each person who, think of it as like, you don't really show it in the picture here, but you could think of each person as being like an X. And so whatever score they get, then they land on this x-axis with, like, let's represent them with a little x. So if you have two people who get the same time, say you have two people who both took 10 minutes to complete the task, you would stack them on top of each other. You'd have an X representing the one person, and then you'd have another X on top representing the other person. And if you had a whole bunch of people who got, say, exactly 10.5 minutes, you might get this tall, skinny curve that we see right here. So all I'm trying to say here to explain to you for sure how to read this graph is that the taller the curve is, or the taller the point on the curve, the more samples, right now I'm talking about individuals, the more individuals that are stacked up there. And that's what this is referring to right here. This flattest curve is the individuals that I just talked about, say 15 individuals, and I put the 15 individuals on this x-axis wherever their score was, whatever their score was. And there could have been 3 or 4 people with the same score, so towards the middle. And so that's how come you get a curve that's tallest in the middle. The hump, if you want to think of it like a hump, is tallest in the middle. Why? Because there's most people at that particular spot. And here we're talking about individuals. But now let's imagine, instead of just grabbing 15 people, we grabbed let's say 30 people, and they become one sample, and we figure out how long it takes each person in that first sample to do this job. And we take, so all these people, we average, we calculate the mean for those 30 people, and the mean um, then becomes where we put their X. So we're going to put an X, not for a single person, but we're going to put an X to represent a whole group of people, a whole sample of people, 30 people. So if we took the 30 people and we measured how long each one it took to do this job, and then we averaged it, we calculated the mean, and let's say it was like 12 minutes for the average, the mean for this group of people. We're going to put an X right here on 12 that represents the mean for 30 people. Let's call that sample number 1. And then we're going to have sample number 2 and sample number 3 and sample number 4. Each one of those samples made up of 30 random people. So what will happen is every time we take a sample, it's going to be a little different than the sample before. So maybe sample number 2 will have a mean of 9 minutes. Sample number 3 will be a mean of 13 minutes. The next sample could be a mean of, it's all random. It's, I'm making it up here as we go. The next one was 8 minutes, and on and on and on. And what happens is you begin to see maybe a curve that looks like this medium tall curve here. And what they have actually here as an example is they're saying that their samples are of 10 workers, right? So maybe I should be sticking with their example instead of kind of making up my own. So let's say that each one of the samples is 10 workers, okay? And it ends up when you stack up all of the results from many, many samples, each one of those samples having 10 people in it, you end up with what's called a sampling distribution that looks like this middle-sized curve. If you, instead of using samples of 10 people each time you do it, each time you take a sample, instead of making it 10, you make it 50, what happens is that you end up getting sort of more accuracy, less randomness. So what happens is you get each one of these samples of 50 gives a result, gives a mean that's closer to the other samples. You get a tighter, taller curve like this one here. This is kind of exaggerated to make a point, which is that yes, you calculate it for 50 people and maybe it's going to be 11, and you calculate it for the next sample and maybe it's going to be 10, and you did it for the next sample and maybe that's going to be 10 again, so you're going to stack that one on top. Again, think of it like X's. And you can see here that there's a whole bunch of samples that are going to be at 10.5, which is like at the center of all of this distribution. This tall curve means you got a lot of samples that were basically 10.5 average. The mean was like 10.5 in each one of those samples, again, based on 50 workers. So what you see happening here, this is, again, hopefully you're getting this. If it's unclear, you could bring this up in class again. It's a little bit difficult to explain because of its abstractness. But the point of this, what's the message they're trying to communicate from this graph, is that the more people that you sample, the closer you're going to be to hitting the truth. You're going to have less error and you're going to have a more accurate sample. Think of it as the bullseye that we talked about before. If you have a bigger sample based on more people, it's going to tend to hit closer to the bullseye because it's going to eliminate some error, some random error that throws things off. See, this individual curve, when our samples are basically of only one person, right? Then your results could be all over the place. You grab one random person, they might take 3 minutes, they might take 15 minutes to get this job done. Who knows? Individuals are going to be all over the place. But when you start collecting samples, either 10 workers or 50 workers or whatever, the bigger that sample gets, the less of this sort of random error that you get, and you get less all over the place stuff going on. It's going to be tighter and closer to the middle, like this sampling distribution where you have 50 workers in each sample, they're all pretty close to each other. You have a tight little narrow curve where your results don't range too much. Basically, if you look at this tight curve, it basically ranges from around 9. The mean for a sample on the low end ends up being about 9, and on the high end about 12. So not that big of a difference from each other, right? Compared to when we're looking at just one individual at a time. You got people ranging all the way from below 3 all the way up to 18 and higher, all over the place. So this is a reality of sampling, that the bigger the sample, the closer you're going to be to the truth, the closer you're going to get to the truth. And that as you get bigger samples, your curve is going to look more and more like a normal curve. This particular graph is kind of exaggerated to make a point. If we move down here, maybe this is the only one I have right here. Yeah, I guess so. I'm not seeing, I thought I had, oh, there we go. See, so here's what you see, that something looks more like a normal curve. And this is a little closer to the truth, that as your samples get bigger and bigger, if you had a whole bunch of samples and each one of them was pretty big, had a lot of people in it, and you laid them out on a graph like this, all of those various samples, think of them as x's once again. You laid them out on a graph like this and stacked them on top of each other if they have the same mean. It would end up, with big samples, you'd end up having a nice normal curve like this. Now, again, maybe these pictures are a little bit inadequate for this, or lacking a little bit. Look in the textbook too to get a sense of what we mean by the sampling distribution. But the takeaway, the most important thing from this, is to realize that big samples are good. That's your takeaway. The bigger the sample, the more accurate you're likely to be, the more likely you are to hit the bullseye. And what we mean by the bullseye is, what's the truth for the entire population, not just your sample, but for everybody. What is the real mean if we're focusing on the mean? Remember, that's called a parameter for looking at the entire population. So if you use a big sample, big sample, you're probably going to get fairly close to the true mean in the population, that parameter, because large sample size tend to create greater accuracy and precision. And you tend to hit closer to the center of that, the bullseye, where the truth lies, the true mean for the population. Okay? Standard error, another term that's not as difficult as it sounds. It's called the standard error, or called the standard error of the mean. This is the standard deviation for sample means. Now, again, more abstract here. So what this standard deviation for sample means is, if we go back to this example here, that if you laid out a whole bunch of results for a whole bunch of samples, the standard deviation refers to how far is your typical going to be away from the mean, the center, right? Or how far away is your random just grab one sample. How far is it most likely to be? What's your best guess for how far away is from the middle? And so if looking at this graph here, it could be like, a typical study could be, say, 2 or 3 points, 2 or 3 minutes away from the center, from the mean. Remember, the mean here is 10.5 minutes to complete the task. That's the average person takes 10.5 minutes to complete the task. And so the standard deviation of the sampling means, or the samples, is, okay, how far is the typical sample away from the middle, from the center, that mean? When we're talking about standard deviation, remember that from the previous chapter, that's how far the typical individual person is away from the mean. Is everybody really bunched up close together? Say it's a test score, and if you have a small little standard deviation, then that means that the students' scores are all similar to each other and they're all kind of bunched towards the center. But if you have a big standard deviation, that's like this flat curve that you're seeing in the graph right here. That means that the students are all over the place. Some people really did poorly on the test and some people aced it and everything in between. And so there's kind of a big gap between the typical student and the center, right? So this standard error has the same meaning. Only here, we're not talking about individuals and how far they are away from the center. We're not talking about individuals. We're talking about samples now, right? Groups of people that that are your sample and that you use to calculate a mean. So it's one level higher. Don't think individuals. Think a sample, a whole group of people, and how far those samples are from each other is what your standard error is. You want your standard error to be small, because what that means bottom line is that whatever the sample that you actually do use, that you do collect, that it's likely to be very accurate and to give you numbers that are close to the truth. If you have a small standard error, if you got a huge standard error, that means who knows what the truth is. The truth could be all over the place. The true population parameter, the true mean, who knows what it is when you have a high standard error, because it could be way low or way high. Standard error means the truth could be all over the place. But if you got a small little standard error, that means you got a narrow little curve and a narrow little sampling distribution, like that tall curve we were looking at. And so if your standard error looks like this kind of a curve, tall and skinny, then when you do one sample, which is what we normally do, in real life, we don't take 20 or 30 samples and then lay them out on a graph like this. We don't have time to do 20 or 30 samples. We do one. But we want to know, is our one sample likely to be really accurate? Is it likely to be off? Well, if you got a low standard deviation, you got a situation like this tall, skinny curve. And so because it's so narrow, your sample that you actually collect is probably going to be close to the truth. It's going to be off maybe a little bit high up here towards the 12, a little bit low down here towards the 9, a little bit off from the truth, which is 10.5, but it's going to be fairly close. If you have a sampling error that looks more like this flat curve, well, then that standard error, I should be saying standard error, is going to be big, and who knows, the truth could be down here towards the 3, or it could be up here towards 18. That's a lot of difference between 3 and 18. So long story short, if this is fuzzy at all to you, make sure and take a look at it in the textbook. But the bottom line out of all of this discussion is big samples are good. Why are they good? Because they give you results closer to the truth. And when I say truth, I mean what's true for the population and not just the sample. So let's see. Trying to decide, we're getting a little bit long here. Let me stop with this last central limit theorem, because it goes along with the standard error, and we'll stop there. The central limit theorem goes like this. As samples get larger, the sampling distribution is normally distributed with the mean equal to the population mean. So as samples get big, each sample that we don't, in real life, we don't do 20 or 30 samples, but just imagine that we did. If those samples are bigger, if they're 50 based on 50 people or 100 people or 500 people instead of 5 or 10, then when you imagine you do all of those samples and you lay them out on a graph, they're going to look skinny like this one because you got nice big samples. They're not going to look, the curve, the layout of all these different samples, laying them out on the graph, it's not going to look super flat and wide, because that's what you get with small little samples. A big sample is going to be narrower, which is in truth, it's going to look like a normal distribution, a bell curve. This is exaggerated here. But the other main point from that central limit theorem is that that as your samples get bigger, they're going to give you means, sample means from your that are collected from your that are calculated from your sample that match up and are the same as the true population mean. That's just a fancy way of saying it's going to give you more accurate results if you've got a bigger sample. You get closer to the center of that curve, which is where the truth is sitting. That's what we mean by central limit theorem. Let me just read that one more time and we'll wrap it up. As samples get large, the layout of the samples, that's all we mean by sampling distribution, is laying them out on that graph, laying your results out on that graph. It's going to end up looking like a bell-shaped curve if you've got big samples. And the mean of that distribution, the average of all those samples, right? Some will be a little bit low, some a little bit high, but you average them all out, and the average is going to hit dead center on the true population mean, right? So, so you might ask yourself, well, what's the bottom line there? What are they getting at with this abstract idea? Bottom line is get the biggest sample you can get and have greater respect for the results from a big sample versus a little sample. Because a big sample is more likely to get closer to the truth. Small samples, you could be way off. We'll talk more about that next time.